We're now going to talk about limits in a little bit more specific way, and we're going to find a few ways of doing it. We're going to find a few ways of estimating limits and finding limits. And we have three basic ways that we do this. So one, let me use that one. One is graphically, two is numerically, and three is analytically. And we're first going to talk about in this section graphical and numeric methods of estimating limits, and they are estimates at this point. With graphically and numerically, we're talking about estimates. And so the first thing we're going to look at, we do need some notation here. We're going to introduce official notation so we can go about this in a straightforward and clear way. This is a definition. And it says a preliminary definition. It is preliminary. It's something to start working with. There are more specific definitions that are much more mathematically rigorous, but right now we're going to use this. And when I say preliminary and it's not as rigorous as other definitions can be, I'm talking about words like near. Okay? We're not sure what near is. What does near mean? It means pretty close. Well, mathematically, there are more specific ways of talking about that, but this will suffice for now. It means generally that if we have a function, and we know what the values of the functions are, let's say we're talking about this point, we're looking at a limit at that point, and we know generally what's going on around this point. It's defined for all points of x. That means all along this x-axis. It's defined everywhere except possibly at this point that we're looking at. We're calling this point where we're looking A. That's what they're using here. It may not be defined there. There may be an open circle there. There may be something going on that we don't know. We can't calculate it, but it doesn't matter what's happening at that point for limits. Limits only care about what's happening right around it, right near it. Okay? So if this is the case, that we know everything about the function that's right around that point, as close as we want to get, okay, very near, extremely near, then we can say that this thing has a limit if it approaches a specific number on both sides, and we'll talk about what that means with both sides. And this is what we're going to be using. The limit of the function f of x as x approaches a equals L. If there is a limit, then it equals L. L is some number. Okay, so let's look at graphically and numerically, but let's look at, I'm going to use Desmos again. This is a function. It's a little bit of a weird function. It doesn't really matter how I created it, what it is exactly. I just wanted to look at it and use it to talk about limits. So let's talk about the limit. Let's say I'm just trying to find an easy number that doesn't look like it's too meaningful. Let's try this number here. I want to see what the limit is as x approaches 0. Okay, so let me write that actually down here in this language. Okay, so I'm looking for the limit of this function. I'm not saying what function it is, but just some function as x approaches 0. I want to know we'll see that, if we can figure that out here. Okay, so here we go. So x is 0 right here, right at this point. I see that just by using Desmos that the value here is 1. I don't care. Limits, as I said, we don't care with limits about what's happening at that point. Maybe we couldn't figure out what's happening at that point. I want to know what's happening as we are around that point. Okay, so as we approach, get closer and closer. In other words, if we look from here to here, 1 unit to the left, 1 unit to the left, I can see that it's going as we're approaching here. It's the value. Remember, the value is the y-axis, the up and down, is getting closer and closer to 1. And if we go from the left, it's going up and it's getting closer and closer to 1. It looks like the limit as we get closer and closer to when x equals 0 is approaching the value 1. And so I might say that that's my guess, and it is a guess because you can't really trust the drawing. We only trust the math completely. So before we go on even further with that, let me introduce a little bit more notation. And we're going to look at the limit as x approaches a from the right of a function, and the limit as x approaches a from the left of a function. What this means here from the approaching this plus mean, if you notice, it's not plus a, it's a, and then the plus is to the right of it, and it's a superscript. It's up there, like where you might put an exponent. Okay, and that means from the right. Okay. Okay, and this little minus here means approaching x approaching a from the left. Okay, so let's see what that means here. And actually, I'm going to do that here. I'm going to say it approaches from the right. We're going to figure out all of these for this function as x approaches 0 from the left of f of x, and the limit as x approaches 0. Okay. Back to Desmos. All right, so again, looking at this point here, I'm just picking out this point because it looks pretty easy. Let's look at the limit as x approaches 0 from the right. That means we're starting up here, okay? It's somewhat to the right of 0. Here's 0. To the right of 0 is, somewhere around here. So let's start over here. And we see that as we approach 0 from the right, that means we're moving left. Don't get confused, left and right. We're coming from the right. We're approaching, getting closer and closer to x equals 0. We see the value is going towards, we can graphically see that it's going down to 1. And you can also numerically, we have the numbers here. Desmos calculates numbers going up here. So you can see that the numbers, the value of the function is 1.71, 1.65, 1.49. As it's approaching, as x is approaching 0, the value is approaching, it looks like it's approaching 1. Right? As we get closer and closer, it's approaching 1. So I'm going to put that in here. I'm going to say, well, it looks to me graphically and numerically, if we put those numbers in there, that from the right, this is approaching 1. It looks like we have a limit from the right of 1. Similarly, from the left, we start somewhere to the left of 0 and we're going towards 0. As we're approaching 0 from the left, you can see the value is 0.7, 0.72, 0.79, 0.85. It looks like it is approaching 1 from the left also. Okay. And so I'm going to put that here. I'm going to say, well, the limit graphically, the limit as x approaches 0 from the left also looks like 1. Okay. And again, this is still estimates and guesses because we can't be 100% sure of really who knows what's happening microscopically close. But the basic thing here to remember that if the limit from the left approaches the same single number as the limit from the right, then we say that the limit exists and the limit is that number, L, whatever number that is. In this case, it's 1. Okay. So that's what I'm checking here. If I'm checking the limit here, I'm first checking from what's happening as we approach that from the right, and it looks like it's approaching 1. Look what's happening when it's approaching from the left. It looks like it's approaching 1. So I'm seeing that it's approaching the same single number from both sides. And so I say it looks like then that the limit as x approaches 0 is 1 because it approaches the same number from the left and the right. And again, we don't have to plug anything into that number exactly to see what the limit is, but we only care what happens as we get closer and closer and closer. Okay, so this primarily, what we just did here was primarily graphic. We're looking at this. I am seeing the numbers there, but I'm pretty much seeing what the numbers. I'm looking visually and seeing what the numbers are doing. Okay. Another way of figuring this out would be to plug in numbers into a function. Let's say we have the function f of x equals 2x plus 1, and I want to find out what is the limit of this, the limit as x approaches 1, let's say, of this function. And we can write either f of x or we can say 2x plus 1. Okay. Well, I can do this numerically. In other words, set up a little chart here. And you can sometimes you're given these charts, you're given the numbers, but just for illustration, I'm going to set up a quick little chart. I want to know what's happening right here, the limit as it approaches 1. And so I'm going to look to the left and the right. What happens at just to the left of 1? Let's say let's go over here, 0.9, right? That's 1/10 below 1, right? If we have 1 here, this is 0.9, 1/10 of a unit to the left. And I'm going to calculate what number that is. And I'm also going to then calculate even closer, 0.09. I'm sorry, 0.99. Okay, that's 1/100th of a unit to the left. And then I'm going to calculate just at 0.999, which is just 1,000th from 1. So closer and closer and closer I'm going to get. All right, so those are the numbers that I'm going to choose just because they're kind of easy numbers to plug in. I'm getting closer and closer and closer to 1 from the left. And I plug in those values into here. Remember, this is not velocity anymore. Now we're looking at values of this function, and we plug all this in. So let me quickly do that with my trusty calculator. All right, so 2x plus 1, that means 2 times 0.9 plus 1. So 2.8 is our first value here, 2.8. Okay. Now I'm going to go a little closer at 0.99. In other words, it's 1/100th of a unit away from the left. And I'm going to plug that into my calculator. So 2, I'm taking this function here, 2 times, and then I'm plugging in this for x. Then it goes in for x. So 2 times 0.99 plus 1 is 2.98. 2.98. And I'm going to do the same thing for 0.999. So 2 times 0.999 plus 1 is 2.998. 2.998. And you can keep doing this closer and closer. I can say 0.9999, or I can use as many nines as I want and get arbitrarily close as I want to 1, and see what's that. So from coming from the left, what does it look like this is approaching? We have 2.8, 2.98, 2.998. Well, to me, it looks like it's approaching 3. Okay, so I'm going to tentatively say 3. It looks like it's approaching 3 from the left. And you can do the same thing on the right-hand side. So 1/10 to the right is 1.1. And I'm going to put that over here, 1.1. Then even closer is 1.01. This is 1/10 of a unit away. This is a 100th of a unit away, and so on. So I'm going to say 1.1. This is 1.01, 1.001, and we can get closer and closer, but this is sufficient. And we're going to plug in these numbers and see what happens as we get closer and closer from the right this time. The numbers are coming from the right. So again, with my trusty calculator, 2 times 1.1 plus 1 is 3.2. Okay, so at 1.1 we have 3.2. Okay, and then we go closer. We're going to now go closer to when x is 1 and plug in the point 1.01. That's only a 100th away. So again, I'm taking my function 2x plus 1, and instead of the x, I'm plugging in my test number. 2 times 1.01 plus 1. We have 3.02. 0.02. And the last one I'm going to use is a 1,000th of a unit away, very close to 1, and plug that in. So 2 times 1.001 plus 1 is 3.002. Okay, so now from the right, what's happening here? As we're moving closer and closer here, it looks like we have 3.2, 3.02, 3.002. It looks like it's getting closer and closer to 3. And if we put in more, even closer units, 1.0000001, it would get closer and closer and closer to 3. 3 and just some small amount. So it looks like 3. It's approaching 3 from the right also. Okay? So I would then say that numerically, it looks like the limit is 3, because the limit from the left looks like it's 3. The limit as x approaches 1 from the left of 2x plus 1 looks like it's 3. And the limit as x approaches 1 from the right of 2x plus 1 equals 3. I'm putting it on the right here. Okay. They're the same. They're both approaching the same signal number 3. So we say that the limit appears to be 3. Okay? That's basically how these limits work. Okay? And again, if you notice, I did not plug in 1. I could, and what would I get? I'd get 3. And it does work sometimes. And we're going to have rules that will give us that exact number. And that's what we call analytic part of analytic finding out limits analytically. But right now we're only calculating them and estimating them graphically and now numerically. So going back here, let's look at an example now of a limits that may or may not exist. So in this case, let's look at when as x approaches -2 here. And we're going to do it visually and a little bit numerically because we have the numbers here. So here's our -2. We want to know what's happening. As we approach from the left, it looks like the value is approaching -1 from the left. And as we're going from the right towards -2, it looks like, again, the value of the function is approaching -1. So from the left or the right, it looks like it's approaching -1. Then our limit as x approaches -2, right over here, as x approaches -2, is -1. Okay. Again, we don't care what happens at that point. We're just looking at what happens as we get closer and closer and closer. If you notice what the value of this function is, well, we have an open dot here, we have a solid dot up here. The value of the function at when x is -2 happens to be 3. So the value of the function is 3, but we don't care with the limit. When we're talking about limits, we don't care about the function at that point. We only care what's happening as it gets closer and closer and closer. So as we get closer and closer to -2 from the left, and as we get closer and closer to -2 from the right, it's approaching the same single number, which is -1. It's getting closer and closer to -1. And we can get infinitely close to that, and it'll still be approaching -1. We don't care what this is up here. Okay? So for limits, we don't care. The limit here is just this. There's nothing tricky going on here. So the limit here would be 1 because approaching from the left and the right gives me 1. And let's look at this one here when x approaches 2. We'll get back to this point here. So when x approaches 2, we're looking at this point here. So as we approach 2 from the left, as x approaches 2 from the left, it looks like the value is approaching 4. And from the right, it looks like as we approach the 2, x equals 2 from the right, it looks again like the value of the function is approaching 4. Left or right, it's approaching 4. So in this case, it's not defined. There is no dot anywhere here. It's just not defined. But again, we don't care. When we're talking about limits, we don't care what happens at that point. That's why the definition says the function is defined all points near except maybe at that point, because we don't care. So the limit as x of this function, the limit of this function as x approaches 2 is 4. Okay? Doesn't matter what the value is, the limit is 4 because we're approaching the same number from the left and the right. Okay? So let's now lastly look at this point here. As x approaches 1, what's happening? Well, if we approach, as x approaches 1 from the left, look what's happening to the values. The value is 1.6, 1.83, 1.84. It looks like it's approaching 2. Okay? Visually, graphically, and numerically, it looks like it's approaching 2 from the left. As we're approaching x equals 1 right here, as x approaches 1 from the left, the value looks like it's approaching 2. What's happening from the right? As x approaches 1 from the right, what's happening to the value? Well, it looks like it's approaching 1. Okay? It's getting closer and closer to 1. So from the left, as x approaches 1 from the left, the value is approaching 2. As x approaches 1 from the right, the value is approaching 1. So the limit from the left is not approaching the same single number. They're approaching 2 different single numbers. Okay? So while the left-hand limit, we call this a left-hand limit, and the right-hand limit exist, the limit doesn't exist because it doesn't approach the same single number from the left and the right. Okay, so visually we can see that this is approaching a 1 and from the right and a 2 from the left. They're not the same. We don't have a limit. Okay, so the left-hand limit is 2. The right-hand limit is 1, but the limit altogether, the overall limit, doesn't exist. Okay, just as a last little interesting example, I'm going to show you another function, just an example of a function um, that's a little bit strange. Okay, so for using Desmos again, I am going to choose a function called, let me see, come on. And let's say cosine of 1 over x. Here, it's an interesting looking function. Okay? And what we're going to look at now, this function has a limit at every single point. In other words, let's say at -2. I'm not going to talk about specific numbers, but when as x approaches -2, as x approaches -2 from the left, it looks like it's approaching this number 0.88 or 0.9 or something like that. And also from the right, it's approaching the same number, whatever number that is. It's not any nice number, but whatever number it is, it's approaching the same single number from the left and the right. And you could do that with anywhere on here, from the left and the right. It approaches the same single number, with one exception. There's one point here where it doesn't necessarily approach the same single number, and that's when x is 0. So if you look at the function here, x is 0 would mean that this was undefined. So this function isn't even defined. We can't have a 0 in the denominator. Cosine of 1 over 0 is meaningless. It's not defined. But if we can still talk about or examine the limit as x approaches x, I'm sorry, as x approaches 0 from both sides. And if they approach the same single number, then we have a limit. Okay? But this number here, look what happens here. What happens as we get closer and closer from the left and the right? Well, here it goes up, then it goes down, it goes up, it oscillates. Okay, we call that oscillating. It oscillates between 1 and -1. It goes up and down. As we get closer and closer to x equals 0, no matter how close we get, you can kind of see it oscillates, but oscillates faster and faster. However, as we're going from the left, I can't get it to do that. To show it's just going to kind of go crazy there. As we approach this function from the left, it's not approaching a single number. It's oscillating faster and faster. It's going up and down and up and down and up and down between -1 and 1. And so it's not approaching a single number like it did with those more well-behaved functions. We can't say it's approaching -3 or 2.5 or any number. It's going up and down. And the same thing from the right. It's not approaching any single number. And so not only do we not have a limit here at x equals 0, as x approaches 0, but we don't have a limit from the left or a limit from the right because they're not approaching a single number. They're going up and down and up and down. The value, remember, that's what we're looking at, the up and down, the y value. Okay, so there are a lot of examples where things don't have limits. And the most obvious and easy kind of functions are functions like this, like just a line, 2x plus 1. We know that's a straight line, and we can look at the limits there. Those are easy. The functions that are more interesting are the functions where we do have some kind of where they're not defined at that point, but maybe we can still get a limit. Those are the more interesting functions. And anyway, that's how we would look at limits graphically and numerically.